Hello everyone. Today's lesson is going to be a little bit shorter than regular. I'm just going to present a couple of ideas and then give you some work to do. So we're going to be doing more work on radicals, and today we're going to be looking at adding and subtracting radicals, as well as rationalizing some more complex examples. But this is not particularly complicated, so that's why it's going to be a bit of a shorter lesson. And it's very similar to some aspects of things we've been doing before when it comes to just regular algebra. So if you need any extra help, as always, let me know. So we have a situation here where we have to add and subtract a bunch of radicals. So this is very similar to the idea of like terms. Okay, it's terms usually involve polynomials, but these are just numbers, so they kind of are still, I guess you can consider them each monomials. Okay, so they behave basically like algebra. The problem is you can't add or subtract roots or radicals unless they have the same radicand. Okay, so like terms equals same radicand. Okay, so the radicand, if you don't remember, is the number that's under the root. And as you can see, none of these have the same radicand, so they cannot be combined together. All right. So let's talk about first making them so that they might have the same radicand, and that is going back to the lessons from the last day or so, which is finding a largest common factor that is also square rootable in each one of these numbers. Okay, so 12 is 4 times 3, 18 is 9 times 2, 27 is 9 times 3, and 8 is 4 times 2. So I'm just writing those underneath there so you can see where I'm getting my final answer from. So the 4 is square rooted to become a 2, and there's a root 3 left over. For the second term, the 9 is going to be square rooted to give us a 3. There's going to be a 2 left over. In this one, the 9 is going to be square rooted to a 3. There's going to be a 3 left over. And then for the last one, the 4 is going to be square rooted to a 2. And there's going to be a 2 left over inside the radicand. Okay? And now you can see that there are what I would call like terms. Okay? Which terms have similar or same radicand? So this term and this term have the same radicand. And this term and this term have the same radicand. So we're going to group up like terms at this point. All right? So the question you're asking yourself is how many root 3s there are. So be very, very careful. We are subtracting and adding here, so we're not changing the type of root. All right? Multiplication and divisions change sorry, not the type of root, but the radicand of the root. Here, I'm just asking you, if you have 2 root 3s and you have 3 root 3s and you're subtracting them, how many root 3s do you have overall? Okay? So 2 minus 3, grouping those two together, gives negative 1 root 3. Okay? So think of it as if you have 2x and then minus 3x, right? The x's don't change. You're just counting up how many you have, which frankly is the reason why negatives and positives in equations are evil. All right? That's basically the whole reason. You have to be able to group like terms that are exactly the same type of thing, and then just count up how many you have without changing the overall thing itself. Okay, so in this case, the thing is root 3. I've got 2 of them. I'm taking away 3 of them. I have negative 1 root 3. And then if we look at the other terms, 3 root 2 plus 2 root 2, how many root 2s do we have? 3 plus 2 is 5. It's still an addition, so you have to write plus 5, the plus specifically, okay? But that is basically all that we're doing for adding and subtracting these kinds of scenarios. Okay, so that's why I'm saying that this is not a very complicated lesson. as long as you understand all of this stuff. All right, so we have to have like terms with common radicands, and then we group up how many we have. So if we look at this one, so again, it becomes a question of how quickly can you write all of the roots so that they are in the proper format. Now these roots do have numbers in front, okay? So I'm just going to quickly write out our factors here. So we have 4 times 5, we have 4 times 3, we have 9 times 5, okay? So the 4 root 3 can't be simplified any further than that. The 4 in the 20 is going to come out in front as a 2 when we square root the 4. That 2 is going to multiply the 3, so it becomes a 6, and then there's a root 5 left over inside the radicand. The 4 is going to square root again to become a 2 in front of this root, leaving a 3 inside. And the 9 is going to square root to a 3, multiplying the 6 out in front. So that's 18 root 5. Okay, so again, if we label our like terms, this and this are like terms, this and this are like terms. So if I have 4 root 3's and I'm subtracting 2 root 3's, I have 2 root 3's left. If I have 6 root 5's and I'm adding 18 root 5's, that's 24 root 5's. Okay? And that's how that works. All right? So, again, just be careful. Don't change the radicands if you're adding or subtracting them. You're just telling me how many there are. So what if we have a situation like this? So this is a situation where we are multiplying through distributivity, again, very similar to regular algebra, the outer thing times the inner things, okay? So we've already seen how to multiply. So the 3 is going to multiply the 2. The root 2 is going to multiply the root 6. So we have 6 root 12. And then we have the 3 multiplying the 1 that's hiding in front of this root. Okay, so 3 times 1 is 3, and it is a 3 plus, it's a positive 3 multiplying a positive 1. And at the same time, the root 2 is multiplying the root 10 to become root 20. And then you want to simplify to check to see if these can group together. Okay, so 12 is 4 times 3. 20 is 4 times 5. So the square root of 4 is 2, is going to join the 6, become a 12. And then the root 3 is left over. The 4 here is going to square root 2 times 3 is 6. Left over is 5. And in this case, they cannot simplify more than that. That is the final simplest form. Now the next question is kind of a warm-up for the question that's going to follow it, but it is still a legitimate mathematical scenario. What happens if we have a case like this? Well, this is just two binomes multiplying each other, basically, right? So we already know that we use double distributivity or FOIL to figure out scenarios like this. But before I start, I do want you to notice that there's an interesting pattern here. You've got the same two terms in both brackets, but one of them's a plus and one of them's a minus. Okay? So what is that going to cause at the end? Well, normally we call those a difference of squares. Is this still a difference of squares? Okay? So we've got root 3 times root 3. Now what does root 3 times root 3 give? That's root 9, but anytime you multiply a root by itself, you can just get rid of the roots, and it just gives you the radicand that's underneath. One of them. All right? So root 3 times root 3 is root 9. Root 9 is just 3. Root 3 times negative root 2 is going to be negative root 6. Root 2 times root 3 is going to be positive root 6. And look at the interesting thing that's going to happen here. And then root 2 times negative root 2 is a minus, right? And then it's a root 2 times a root 2, which is just 2. It's root 4, which gives 2. Now, what happens to those two middle terms? Well, those two middle terms become 0. All that we're then left with is 3 minus 2, in this case, giving us 1. So what happened is we had two root-filled brackets multiplying each other, and we end up with a rational number as our final answer. We're going to use this technique to rationalize the next example. So this is a scenario where we need to rationalize, and the reason we need to rationalize is because one of the rules we saw in the previous lesson is that you're not supposed to have roots in the denominator of a fraction. But because this is a subtraction, we have to use the previous example as the way that we're going to rationalize this. If you have multiple terms, a binom, for instance, in your denominator, with a plus or a minus, we have to use a way to get rid of that. Well, look at what we did here. We used the same bracket as itself, but with an opposite sign, right? That is called the conjugate. So we're going to multiply by the conjugate of the denominator to rationalize. Okay? So I'm going to put a bracket around here, and I'm going to multiply the entire thing by 2 root 6 plus root 3. But as soon as I do that on the bottom of the fraction, I immediately have to go up to the top of the fraction and do it there as well. That doesn't change. Okay? Anytime you do something to the bottom of a fraction, you immediately have to do it to the top of the fraction. But by multiplying by the conjugate, we've got that scenario similar to, I'm going to go back to this slide again, to this example, where those two are going to multiply to get rid of the roots and give us a rational answer. Okay? And if you look at the pattern, you're basically just squaring the first number and squaring the last number, because the two middle terms of FOIL are always going to cancel out. So I think we can save us a little bit of time by not foiling this bottom and just using that property. We're going to square the first number. We're going to square the last number. It's going to be a subtraction. The top will distribute. Okay? So what do we get for the top? We get 10 root 6 plus 5 root 3. The 5 multiplies the 2 in front of the root. The 5 multiplies the 1 in front of the second root. For the bottom, what happens when we square 2 root 6? So I'm going to write that off to the side. Okay. Now, this is 2 squared, if we look at it the long way, times root 6 squared. That is 4 times 6. So the first number is squared. The root is also squared, but when you square a root, all that happens is the radicand gets pulled out. Okay? So if you can start to get used to that, you don't have to write it out. Of course, as always, showing more steps is not a bad thing. But I feel like most of you should be able to do this once you get a little bit of practice. So it'd be squaring the first number 2 to give us 4. Because I did this off to the side, I'm just going to write the answer. So the full answer is obviously 24. Squaring the second one's a little bit easier because it's just root 3. There's no number in front, so the square of root 3 is 3. Now, I can't tell you how often, folks, that somebody will write 9 at that spot. It's very tricky, right? You have to remember that you're getting rid of the root only by squaring it, which gives us the radicand, which is 3. Okay? So, what do we end up with? Well, just to quickly check, is there any way we can simplify this root 6 at the top? there's no factor of root 6. There's no factor of 6 that is square rootable. So that is already in its simplest form at the top. So we've got 10 root 6 plus 5 root 3, all divided by 21. Now there is one final thing you should check, folks. The 10 and the 5 are technically factorable. But the only reason I would want to factor them is, are they also divisible? Is the factor of 10 and 5 also divisible by 21? And the answer here is no. Okay? But you can always check to see, is the top factorable? And specifically, can it also, so and, that's a terrible and is it simplify, is the factor able to simplify with the bottom? Okay, so it is possible to go a little bit further. This example doesn't show that, but you're used to factoring things, and we have been seeing that sometimes it's better to factor if you're trying to simplify these. I showed some examples of that the other day. So just check to see with the denominator, is it worth factoring the top? If it's not worth factoring the top, just leave it as it is. But if it is worth factoring the top, you have to do it, or it's technically not simplified to its maximum value. And that's it for today's lesson, folks. I'm going to post some homework to go along with that lesson. And please get that homework practiced and done. And I will see you on the next lesson. So have a great day.